What's going on, YouTube? Welcome back to the Thomas Gallery, and today I want to talk about stars. Not stars as in superstars or Hollywood stars, celebrity stars. No, I mean actual stars, celestial bodies in the night sky. Okay, now, what are stars? What are they? You hear about them all the time. A lot of people don't know what they are. Well, simply put, stars are really hot gas. Not hot gas as in flatulence. I mean hot gas as in elements such as hydrogen, helium, all those things, okay? Now, what makes a star? Well, a lot of things make a star, but overall it's just the gravitational force when stars explode, and they do explode, called a supernova, boom, exploding star. The remnants of those stars fly out into space. Here, there, everywhere, every which way, back, forth, about, down yonder. And over time, they come together through the force of gravity. They come together, one gas particle at a time, at a time, at a time, at a time, and at a time, and over a period of time. When I say a period of time, I don't mean 5 minutes. I mean over an extremely long period of time, longer than the human lifespan. Okay, longer than human existence. This these gas particles come together, and they form a little spherical type object due to gravity pushing it in on all sides. Okay, and over time the gas builds up, builds up, and builds up, and builds up, and through that through that buildup of gases, they begin to heat up, because once you condense something into a small amount of space, a lot of energy is being exerted into doing that, which heats it up. But this, if any of you ever had a a rubber ball, like you know how like, you take a bunch of rubber bands and you tie them all together and tie them all together, make like one big ball and they get bigger and bigger and bigger. Well, here's the thing: inside of that ball of rubber bands, it is hot, okay? Because of the forces, the friction, the pushing, the pulling, all that going together at the same time, the stretching, the bending, all that stuff is hotter on the inside than it is on the outside. Okay, and how you know that? Because if you were to cut open the ball of rubber bands, you could feel it be hot on the inside. Okay, well take that and just think about that rubber bands being gas. The gas is building in on each other constantly, 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 until the center is getting so hot, it does what's called fission. Well, I'll play this. The fission and fusion happen at the same time. The core gets so hot that it starts to make other elements, and that force requires a lot of energy, and that energy has to go somewhere. It has to go somewhere. Energy doesn't like to be put in one place. Energy likes to be free. It likes to flow. It doesn't like to be in one spot, staying there. Okay, it likes to be out and about. So it exerts a lot of energy. The energy that's pushed out is fission. The energy that goes together that can make new elements is called fusion. Fusion is the bringing together of objects. In this case, gases to make elements, and you got hydrogen, helium, all the way up to you got hydrogen, helium, oxygen, right? Nitrogen, no, hydrogen, helium, lithium, nitrogen, oxygen, carbon, and it goes all the way up to the elements in the element chain. Adding a proton, which adds an element. And because of this process, the stars give off light, heat and light, a lot of heat and a lot of light. Okay, so much so that depending on where you are, you can see the brightness of the star at night. Now, do we know of any stars close to us? Well, yes. Matter of fact, we do. It's called the sun. The sun that you see in the morning time, that you see out that cooks your brain on summertime, right? It's a star. It's the closest star to the Earth, okay? And that star has a force that brings planets together, okay? 8 planets, plus some other celestial bodies, some asteroids, some meteors, some comets, some planetoids, all that stuff, okay? Which makes a solar system. Okay, now I'll talk about solar system at another video, but right now I'm talking about just what a star is. Now there are different types of stars. You have your regular yellow star, like we have our sun. You have your white dwarf, which are smaller by comparison to our star, but it is heavily dense because what a white dwarf is simply just when a star explodes. Okay, when a star explodes, it leaves behind the core. That thing I was telling you about earlier that builds it on itself constantly. That core, the center of the star, it leaves that behind, and it is so dense. Like you have a neutron star, all that stuff. It's the core of the star. Okay, it is so tightly dense that it's gone way beyond the temperature of our sun, our star. Then you have your red giants. Red giants are older. Red giants are on the cusp of dying. They're right at the cusp of becoming a supernova, which is an exploding star. Okay, they're there. They can be massive. They can be they are like 100 times, millions of times bigger than our star. Okay, our star compared to a red giant is like the equivalent to the moon to Jupiter. Put our moon next to Jupiter, it'd be like that. Okay, so that's just how that go. And that there are other kinds in between those, but like the main kind, like we got your white dwarf, you got your yellow sun, you have your red giants. Now there are other kinds of stars in between that, but the three main ones is white dwarf, yellow sun, and red giant, big red giant. We have a yellow star, and which means in terms of age range, that is kind of young. It's kind of young. The red giants are old. Our star is relatively young, but by young I don't mean well, someone is 32 and then you have a newborn baby. No, no, no. If you want to talk about the equivalent, I apply it like this: a red giant is a senior citizen compared to a child. Okay, like that gap. Okay, that gap. So our star is pretty young, about 4.6 billion years. That's young in terms of macro time. Now it's far beyond our regular GPS digital watch. No, we're talking about macro time. We're talking about universal scales. We're talking about billions of years and millions of years beyond. 30 seconds. You can't even think about 30 seconds when you're talking about billions of years. Okay, our sun is about 4.6 billion. Okay, well, no, our Earth. Our sun's a little older. Our Earth is about 4.6 billion. Our sun is a little older, but still relatively young. Okay, so you know that's my little spill on stars. Drop a little something on y'all. Hope y'all enjoy that. I catch y'all later with some more stuff. I got some more stuff to talk about. I see you all later. All right? Peace.